Bastiaan Cijsouw. So he is at TenET, the Dutch-German TSO, where he's been since 2018, working in system operation and international development, including actually some of the same topics that Pierre has been talking about. So I'm going to try now to share with everybody Bastiaan's pre-prepared presentation and find the right window and click the right button. So it should be there, it should be optimized, there we go. So I hope everybody can see that. Somebody speak to me and say yes, and I'm going to press play.
The paper that will present this presentation is called Computing a Nodal Power Exchange Matrix based on a Nodal Reactance Matrix. The authors are Bastiaan, that's myself, Susana, Almeida, Graaff, and Jasper van Casteren. And we all work at the development team at System Operations of TenET TSO the Netherlands. In this presentation I will first tell something about the context, then we will dive into the methodology that's explained in the paper, and in the end we will look at some interesting results. In 2017, TenET TSO developed the full-line decomposition methodology to decompose flows based on the cause-effect principle. So consider a flow over a Dutch branch, then FLD is able to decompose that flow into partial flows, for example flows from Dutch generators to Dutch loads, which we'll call internal flow, and so on. FLD has multiple applications. It's one of the candidates for the flow decomposition tool for the redispatch and counter-trading cost sharing in the core region. It's also used operationally to calculate loop flows, and it's used to identify the green flows in the network. That will be flows from wind parks or solar parks. How does this flow go to the network? In this slide, the FLD calculation process is displayed. If we start at the top left, we see the input of the FLD methodology, which is only a network model containing the topology, the branch impedances, the generator dispatch, and the load demand. If we go down, we arrive at the nodal PEDF matrix. That's the power exchange distribution factor, which is calculated as the PDDF of one node minus the PDDF of the other node. And what does it mean? It's the megawatt flow over a branch as a result of an exchange of 1 megawatt between two nodes. If we go from the input to the right, we see the nodal power exchange matrix, which is a full specification of all the power exchange exchanges in the network. So one cells means the power exchange from node I to node J. And multiplying the PEX matrix and the PEDF matrix gives us the nodal PFP matrix. For every branch in the network, we have the megawatt flow as a result of the exchange of two nodes in the network. The nodal PFP matrix can be aggregated to a zonal PFP matrix, where each cell represents the megawatt flow over a branch as a result of an exchange between two zones. And finally, we can even aggregate that matrix to assign flow types to each branch, and also compute the PST cycle flow by the PSTF and the PST stop settings. The most important parameter of the FLD methodology is the power exchange matrix. So let's look at the definition of the power exchange matrix. It has the dimensions of the number of generators times the number of loads. Each cell of the matrix is non-negative. We have that rho I adds up to the total dispatch of generator I for every I, and also that column J adds up to the total demand of load J for every J. So when we look at the example network model, we see 4 generators in red and 5 loads in green. And this is a PEX matrix for this example network model, because each cell of the matrix is non-negative. We have that the rows add up to the total dispatch of the generators, and we have that the columns add up to the total demand of the loads. And currently the PEX matrix in FLD is computed via the BLEC flow tracing algorithm. So it traces the flow from the loads to the generators, and this is in fact the resulting PEX matrix for this methodology. However, any PEX matrix could be applied in FLD and would give consistent flow decomposition results. So, the aim is to calculate a PEX matrix based on reactances. So now I will explain the methodology of the paper. First we look at some assumptions, namely that we're working with a balanced network with N generators and M loads. We assume a linear load flow, so that's a load flow without losses. However, we can attribute the losses of the branches to the adjacent nodes. And we assume that the effective reactance between every pair of nodes is greater than 0. Then we define Cij to be 1 over Xij, and we call that the electrical proximity between generator I and J. And the objective of this methodology is to calculate the PEX matrix only using the nodal proximity matrix C, the dispatch of the generators G, given in the vector of length N, and the demand of the loads L, given in the vector of length M. And the power exchange should be approximately proportional with the proximity. Methodology, we will define PEX Ij to be A times Gi times Lj times Cij, where A is a real number greater than 0, G is a vector of length N and the sum of the elements is 1, and also L is a vector of length M and the sum of the elements is also 1. And AGL is a solution of the following equations. Well, the first equation assures that each row of the matrix adds up to the total dispatch of that generator for every row of the matrix. And the second equation assures that each column adds up to the total demand of that corresponding load for every column of the matrix. So we're looking for a solution AGL that satisfies both equation 1 and 2. However, it can be shown that this is equivalent with finding a solution L of length M satisfying equation 3. And a solution to this equation can be found iteratively. So we define L0 and we define Lk plus 1 in terms of Lk and Lg and C. And an algorithm to find the solution L, and therewith also a solution AGL, was implemented in MATLAB. Now we will look at the result of the methodology. Therefore we look at the example network model, where the reactance of every branch is equal to 1 ohm. So we can compute the proximity matrix C for this network model, which you see in this slide. We also have the generator and the load factors for the 4 generators and the 5 loads. And then running the algorithm gives AGL, which are given below. And in this way we can define the PEX matrix to be PEX Ij is A times Gi times Lj times Cij. And the PEX matrix is given in this slide, and we see it's indeed a PEX matrix because every cell is non-negative. We have that the rows add up to the total dispatch of the generators, and we have that the columns add up to the total demand of the loads. So for comparison, 3 PEX matrices have been computed. That's the proximity methodology, which is explained in this presentation. So the PEX Ij is A times Di times Lj times the proximity Cij. We have also the equivalent bilateral exchange matrix, which is only depends on the generator dispatch and the load demand. And finally we have the BLAC PEX matrix, which is defined via flow tracing. So when we look at, for example, the exchange in the proximity PEX from B4 to C2, we see that it's a relatively large exchange, and that makes sense because also in the network model B4 and C2 are located close together. For EB equivalent bilateral exchange, we have that all the exchanges are proportional with the generator and the load. And for the BLAC, it's based on the flow tracing. And one thing to note here is that, for example, generator A1 and A2 are very close together in the network model. However, their PEX exchange looks totally different. While in the proximity PEX, the dispatch of generator A1 and A2 is quite similar. In order to measure whether the exchanges are indeed proportional with the electrical proximity, we have to correct for the generator dispatch and the load demand. So therefore we define the normalized exchanges to be Nij is defined as the PEX Ij times the total dispatch divided by Gi times Lj. And that's exactly the same as dividing the PEX matrix by the equivalent bilateral exchange PEX matrix. Some observations. We see that for equivalent bilateral exchange that the electrical proximity is independent from the normalized exchanges, which is exactly what we expect. For BLAC we see both 0 and very high values for Nij. And for the proximity PEX, we see that the normalized exchanges are indeed approximately proportional with the electrical proximity. We have also applied the methodology to the full ENTSO-E network. That in this case is a D2CF network model of the 22nd of January 2018, 8:30. And there are more than 1600 generators, more than 8800 loads. The total exchange in the network is 271 gigawatts. There are more than 16,000 branches, of which nearly 100 PSTs. And there are 31 bidding zones in the network model. And the graphs at the right show the normalized power exchange for the exchanges larger than 0.01 megawatt. And note the logarithmic scale on the axis. So on the horizontal axis there we have the electrical proximity, and on the vertical axis the normalized power exchange. Some observations. The equivalent bilateral exchange, we have that the electrical proximity is independent from the normalized power exchanges. For BLAC, we don't see a clear relation between Cij and Nij. And for the proximity PEX, we have that the normalized exchanges are indeed approximately proportional with Cij. And the computation time of the proximity PEX is within 0.5 seconds. However, computing a full nodal reactance matrix may take several minutes for this network model. Here we're looking at flow decomposition result for a Dutch 380 kV branch. The total flow is 555 megawatts. Some observations is that for the proximity result we see large contributions from Germany and the Netherlands, and also significant contributions from Spain, Italy and Poland. While for the BLAC we see also major contributions from Germany and the Netherlands, however very minor contributions from the other zones. And all the methods show relieving contributions from France and Great Britain. Then we arrive at the conclusions. So we have proven that we can compute a power exchange matrix based on the reactance matrix. The only input is the generator dispatch, the load demand and the electrical proximity. we have that the Pax matrix is approximately proportional with the electrical proximity. The method gives consistent results. The method is computationally efficient, and the resulting Pax matrix can be applied in the FLD methodology. And further development includes a formal proof of existence and uniqueness of the Pax matrix solution. And we also want to extend the experience calculating Pax matrices for the ENTSO-E network. This is the disclaimer. This is the last slide.
Okay, thanks very much. I think we're back from the video display now.
You're back live again.
Yeah, you join us live from. So we've got a couple of questions on the Q&A,
Yeah.
and I think they're related to kind of what are you using this for? I think that's the first question. Like you're trying to get this relationship, a bilateral transaction, a generator or a load. If you increased, the generation to meet a certain load, which might be at a node or at a country level. What's the idea? Is it to see how big a transaction could be accommodated, or alternatively, as it seemed to be implying in the last slide there, is trying to see what is the impact of different transactions on a particular line. So, how are you using this? And that might help to explain the answer to the next question, which is what is the right approach out of the three you've talked about?
Yeah, so it's used to find the cause of the flow over a network element. So for example, you have a network element which is overloaded. You want to assign the causing zones to that overloaded line. For the cost sharing, for example. So if there's a mechanism of cost sharing, then the costs of the redispatch can be attributed to the causing zones of the overload.
So in principle, it could be addressing that problem we discussed with Pierre just at the end, about the redispatch, who picks up, the tab for it. That's the kind of the main purpose that you envisage.
Yeah, exactly. Yeah.
So in terms of which of these three methods, are kind of fair in doing that apportioning of the cost, or most fair,
yeah, exactly.
Which one is your final big conclusion then?
Yeah, we want the method to be fair, and therefore we want to have it based on physics. And we think that if you base the Pax matrix on the reactance in the network, that's a really physical parameter, and that will be a very fair way of attributing the flows, and therewith also the costs to the causing zones.
Yeah, although obviously you've constructed that for a particular topology of the network. So maybe what looks like the cause of a particular flow in the intact condition might not be the same as it would be if there was an outage. And perhaps the dispatch is actually caused by the outage condition, not the intact condition. And it might give you a different sharing factor.
Yeah, but that's already included in the full line decomposition methodology because every n-1 outage can be taken into account. And in that situation, the flow decomposition is computed.
So it's going to be computed for the critical outage, I suppose, hasn't it?
Yeah.
If you know what the critical outage is.
Yeah, beforehand it's sometimes a little bit difficult, but yeah, for every critical outage you can compute the flow decomposition. Yeah.
Okay. Well, thanks very much. I think we need to move on. We've had a bit of a chance to discuss. I didn't see any more questions coming in, so well, now thank you very much, Bastiaan.